So I am out today. So here is a video for the lesson that we are working on today. Today is 01/29. Today's the 29th. And we are working on investigation 1.3 and finishing 1.2. So we're finishing 1.2 and working on part of 1.3. We're not going to do all of it. We're just going to do some of it. Today, actually, let me highlight this so you know which one we're working on. So we're working on this and finishing 1.2. This is the new one for today. Down here is additional practice 1.1 and the AFQ for 1.1. Tonight's homework date assigned is 01/29. Additional practice page 65 and 66. Additional practice page 65 and 66. Also answer your AFQ for 1.2 and 1.3. Okay, that should be due next class, which will be tomorrow. Remember, tomorrow is an all period day. You are going to see all 6 classes tomorrow. So you will see my class tomorrow, and you don't have to write this part down, but there is a quiz Thursday this week. Thursday 01/30. So there's a quiz this coming Thursday for everybody. Okay, so just a reminder, it is the 31st, not the 30th, the 31st. Okay, it's right here. See quiz 30, quiz on the 30th. All right, so just a quick review. We just finished 1.1. We started 1.2, and we were somewhere around here. Okay, so question B we answered was over here. Okay, so it's going to ask us to graph the times and distances for all 3 students on the same coordinate axis. So graph the times and distances of all 3 students on the same coordinate axis. Okay, so we got 2 variables here. So here are 2 variables. We've got time and we've got distances. Those are the 2 ideas that we're going to be working with from our on this graph and from this table. So I'm going to take a quick snapshot of this table here, so that way I can put it next to our graph. Oops, let's try that again. That's better. All right, so it says distance and time. So those are the 2 ideas we're working with. Here's our distance, okay? And distances are always defined by, in this equation, they are defined by our y values, and our x values are defined by our time, okay? That's why this is in red here, okay? And the rest of these are blue changes, and the distances is listed up there as y, okay? So this should be an x value here. All right. Now, I'm going to work with Alana, and Alana's is in this dark blue color, okay? Alana, here's Gilberto in green. Gilberto. These characters or people in our story actually show up in the 8th grade book as well with a very, very similar story. So it's important that you understand what they are doing. Okay, so let's work with Alana first. And Alana has a graph at 0 seconds. She's at 0 meters. So Alana starts off at 0, 0. At 1 second, she's at 1 meter. So 1 second, she's at 1 meter. At 2 seconds, she's at 2 meters. She's here. At 3 seconds, she's at 3 meters. There she is. She's moving along, and her data makes a nice pattern and a nice straight line up to 10 seconds. So this is Alana, and we can connect our dots. Okay, and there's Alana. Gilberto starts off at 0, 0 also. 0 distance, 0 seconds. Here it is. At 1 second, he's at 2 meters. So 1 second, he's at 2 meters. You can pause the video here so you guys can finish the graphs, finish Gilberto and Leanne. Okay, so go ahead and pause the video, work for about 5 minutes or so or less, and then hit the play again. All right, at 2 seconds, Gilberto is at 4. At 3 seconds, he's at 6. At 4 seconds, he's at 8, 10, 12, 14, 16, 18. And then we're a little bit off the charts after that. There we go. That's Gilberto. And here is Leanne. She starts off with 0, 0 also. Then she goes to 2.5, somewhere around here, but it's kind of hard to graph. So I'm just going to go to 2 where she's at 5. That one's a lot easier. At 4, she's at 10. At 4 seconds, she's at 10 meters. So at 4, she's at 10. And at 6 seconds, she's at 12 meters. 6 seconds, she's at 12 meters. What? 6 seconds, she's at 12. Sorry, at 4, she's at 8 meters. So this one is off. This should be 4, she's at 10. Sorry, I got that right. 4, she's at 10. And then at 6, she's at 15. I was looking at the wrong one. 6, she's at 15. Over here. Okay, and I can connect these dots. Oops, a little bit of a crooked line there. I skipped every other because it was hard to find those other points. Okay, so you're going to be working on questions A and then 3. That was 2A and then 3. And then, where are we, 16? Yeah. And then we'll do 4, 5, 4, 5. And then we'll go down here to 2 and 3. Okay, 4, 5, 2, and 3. Okay, so A, 3, 4, 5, number 2, and number 3 on page 17. Okay, all right, so go ahead and pause the video, set a timer for about 15 minutes. Should be able to finish most of these in about 15 minutes. Okay, there's a timer on my desk if you need it. Pause the video. All right, so after your video's paused and you hit play again, how does the walking rate affect the graph? Okay, and this one is the steeper, or the faster the rate. The faster the rate, the steeper the graph. Okay, so faster rate, and rate is considered speed. So the faster they are moving, the rate is higher. Okay, you have a steeper line. Okay, the slower it is, if it's going a little bit slower, slower rate or slower speed, okay, the less steep the line is. Okay, so in here we have Alana. She's going at the slowest speed, so hers is the flattest of the bunch here. Okay, and here we have Leanne. She's going the fastest, so hers increases the most in the quickest amount of time. Okay, so she's going very, very steep. Okay, so it says write an equation that gives the relationship between time and distance for each student. Okay, so I'm looking for an equation between time and distance. All right, well, if we look at page, I believe it's page 12, there's an equation that looks like this. Distance equals rate times time. Rate times time, or t. Okay, so let's start with Alana. Here's Alana's equation. Alana has distance equals rate times time, and her rate is 1 meter per second times time. Okay, times time. Let me fix this. Okay, and this is for Alana. Okay, here's Gilberto. Okay, Gilberto has a rate or distance that is equal to 2 meters per second. Okay, 2 meters per second times time, and the time here again is just time. We don't know how much time has passed. It could be 1 second, it could be 10 seconds, it could be a million seconds. I abbreviate it with just a T. And lastly, we have Leanne. Leanne has a distance that is equal to 2.5 meters per second. 2.5 meters per second times time. Wrong color. Times time. All right. 4 says, how can you predict that the graph will be straight from a line, will be a straight line from the pattern in the table in the equations, and explain. All right. So again, these values here represent our x values. Okay. These represent x variables. Okay. X doesn't look like an X. X values. These are our independent, and these here are our y values. Okay, and these are dependent values. Okay, so you need to have a pattern of change in your table that's consistent. So here, this is a plus 2.5, plus 2.5, plus 2.5. Here, this is a plus 2, plus 2, plus 2, etc. This one is a plus 1, plus 1, plus 1 as we move along. Okay, and then over here we have a plus 1, plus 1, plus 1. Okay, so in an equation, or sorry, in a table. Okay, so if the pattern is the consistent, so if the pattern is consistent, actually let's change that. If the pattern of change in distance, and I'm going to highlight in blue distance because distance represents these ideas. Okay, if that's all the same all the way through, is the same. This should be y values. If our is the same for every x value, or seconds for every time, which is our x values, then the line will be straight. Then the line will be straight. Okay. In a graph, this one's really easy. Oh, does it ask for the graph? Well, the graph is easy. Let's just write that really quick. Graph, if it makes a straight line. If it makes a straight line. Straight line. And lastly, if you have an equation, so to determine if you have a straight line in an equation, you have to check to see if it has a constant of proportionality. If the equation has a constant of proportionality. Okay, and the constant of proportionality shows up in an equation like y equals For example, Gilberto is 2 meters per second. I'll call that time. And you know what? I should use the same signs I was using earlier. Okay. If it has a number like this, a constant proportionality or a slope or a rate, then it is a straight line. Okay. All right. Number 5, are there any of these proportional relationships? If so, what is the constant proportionality? Okay, so all of them are proportional. They are all proportional. They are all proportional. Okay, and the constant proportionality is the amount of change in distance and change in time. So here for Alana, her change in distance was 1 meter for every 1 second. Gilberto is 1 meter for every, 2 meters for every 1 second. And Leanne is 2.5 meters for every 1 second. Okay. Thank you. Okay, so for each student, if the time changes by 1 sec, did I ask for this one? No, let's do this one. Okay, so number 2 says if t increases by 5 seconds, how much does the distance change? Okay, so let's write some ratios here, or some proportions. Here is Alana. Okay, Alana does 1 meter every 1 second, and we want to go 5 seconds more. So we end up with 5 seconds. They will travel 5 meters. Okay. For Gilberto, he will go 2 meters every 1 second, but we want to get all the way to 5 seconds. So I'm going to multiply by 5. I'll multiply by 5. And we end up with 10 meters every 5 seconds. And Leanne will set up the same way. Leanne will go 2.5 meters every 1 second. And we got to get to 5 seconds. 5 seconds. And that means that they will go 12.5 meters in 5 seconds. Okay. Number 3 will be set up the same way. The key word here is per minute. And per minute is the same thing as 60 seconds. So 1 meter for 1 second times 60 over 60 will give us our 60 seconds we are looking for. 60 seconds, and she will travel 60 meters. Okay. Gilberto will do the same thing. 2 meters every 1 second, and we want to go 60 seconds or 1 minute. We have 120 meters in 60 seconds. And lastly, we have Leanne, who goes 2.5 meters every second, and we'll multiply by 60 over 60, and we get 180 meters for every 60 seconds. Okay. Actually, we're going to answer question C too, so this one's important. So answer question C, pause the video, go another 5 minutes. Okay, so after pausing for 5 minutes and you have given the work a try, we're going to identify if these relationships are linear. Okay, so we need to make sure when they're asking for a linear relationship, okay, all they're really asking is, does it make a line? Does it make a line? All lines are straight, so they're not asking if it's making a straight line, because if we say line, we mean straight line. Okay. All right, so I need to find a pattern of change. Here I have plus 1, plus 1, plus 1, so plus 1, plus 1, plus 1, plus 1 every single time. Okay. Now I have to see if there is a pattern on this side. Here I have plus 2, and then I have plus 7, and then I have plus 2 again, and then I have plus 9, and then I have plus 5. Is this consistent? Is it a pattern there? Is there any sort of pattern? No. So since this one has no pattern, then this one is non-linear. Non-linear. Okay. Here's Elizabeth walking rate. We'll do the same thing. This is a plus 2, plus 2, plus 2, plus 2. And over here it's a plus 3, plus 3, plus 3.